I picked two different variations. The first one is fine-tuning it on photorealistic images. There are only 20 images of my dog in this data set and got pretty impressive results. The other example that we're going to do, which it didn't do as well on, was all right, welcome everybody to Fine Tuning Fridays with Oxen.ai, where today we're going to dive into fine-tuning Flux and specifically FLUX-1 Dev. And as I was diving into this model, there were a few open source repositories that I saw to train this thing. There was one called AI Toolkit, which you guys might have seen. This one actually gave me the best results when I was using it, but it's pretty convoluted code and works with a lot of different models. So there's a lot of like nested if statements to get to the core of how to fine tune just the Flux model. There was a simpler example on Hugging Face, but I couldn't quite get that code to actually generate anything coherent. So I decided just to like break this down step by step and write the code from scratch. So we have like a very self-contained, it's about 500 lines of code to fine tune this model. And that's what we'll be walking through today. So I think it'll be really good to kind of see how the ins and outs of this model work, give you kind of the confidence to train these things or even write the code from scratch. And I think there's some interesting takeaways that we can dive into as we go through. If you haven't seen the Flux model, it does generate super high quality images. It was released about 9 months ago, and there's a suite of models that they released. They actually released a new one yesterday as well, which we can talk a bit about. But if you go through the list of models, they have FLUX-1 Pro, which they claim is the best one, but is sadly only available behind their API. They have FLUX-1 Dev, which is an open weight model. It was distilled from FLUX-1 Pro and gives similar performance to Pro, but you do need to contact them for a commercial license. So you can use it for research, you can use it for stuff like this or internal use cases. But if you're gonna like sell it through an API or build on top of it for your company, the license is actually pretty expensive. It's $999 a month for the license. They did just add like a self-serve portal to get the license yesterday. So I checked that out and it was pretty expensive. They have FLUX-1 Schnell, which is the fastest version of all of these and open source and Apache 2.0 license, which is great. But this model is step distilled. It's what they call step distilled. So this is cool because it can generate images in just a few steps instead of like, your normal distillation process. Maybe you're taking 30 steps to get rid of the noise. This can do it in, 5 to 10. But it also makes it harder to train or fine tune because it has less of those noise steps to train on while you're going through it. There are some adapters to train this one. I actually stuck with FLUX-1 Dev because it is a higher performing one than the Schnell, and just wanted to give like the most simple version of the code that we could walk through. And so the day, like literally yesterday, before I was writing all of this, they dropped a new model called FLUX-1 Kontext, which we can look at here. And what's cool about this is it's really good for editing images and character consistency. So you can see it's like remove the thing from her face. There's a snowflake on her face. There's it removed. She's now taking a selfie in the streets of Freeburg. It's a lovely day out, and it's the same character. It's now snowing, it's the same character. So super impressive. I did try the demo out a little bit yesterday, but I ran out of credits pretty quickly. And I was really impressed with what it did with my dog. So this was the input image here. And I said, make him surfing and put it on a surfboard. It kept the leash and stuff like that, which was funny, but that's definitely my dog on a surfboard. And then I had him playing chess while smiling, looking at the camera. And like these photos, I mean, they are hyper realistic. That is definitely my dog. Super impressed with the couple examples that I tried out. Even this one, which was like the original one, I said, make the dog playing chess. You can see the backgrounds of the images. You know, look at the palm trees right here, look at the grass. When it added the chessboard, it maintained all of that detail in the background, which is uh, pretty impressive. My girlfriend walked over while I was doing this, and she actually thought this was the reference image that I put in, not the image that was generated. So this one, they just dropped the weights on Hugging Face for, and it has a similar license, or it has the same license as um, the FLUX-1 dev. So it's restrictive. You have to pay $9.99 a month for it, but pretty impressive. So the tasks that we're going to be doing today, I picked two different variations because the first iteration that I worked on, it actually didn't work very well on, and I think that's going to be interesting to dive into. But the first one that we'll go through is fine-tuning it on photorealistic images, so like ones of my dog. This was a data set that I put together that was actually pretty small because I wanted to push the limits of how many examples we needed. There were only 20 images of my dog in this data set, and I trained it for like a couple hundred steps and got pretty impressive results. You can see here's him drinking some coffee. Here's the chess scenarios again, DJing in a nightclub. And I feel like it really captured, I mean, I know my dog pretty well, and these are like the poses that he would sit in and how he would smile from the side. So I was pretty impressed with those results. The other example that we're going to do, which I would argue it didn't do as well on, was we're trying to put together a vector graphic Ox character. And here are some reference images on the left that I had in the training data set. And you can see after a decent amount of training, and I had 400 reference images here, it still couldn't quite pick up like the coloring or the shape or the outlines or even the facial expressions. I definitely did like a white ox character, but not as strong as I would hope. And I think I have some theories as to why. But comparing this to the PixArt model that we did a couple weeks ago, PixArt actually nailed this style of character. So this is the same training data set, just a different model, PixArt Alpha. And you can see like these are the training images, and then these were the ones that were generated. And these definitely have the body shape and the texture and the line. And I was actually pretty impressed with what PixArt did, which is interesting because it's a much smaller model, way faster to train, actually. This one is Apache 2.0 license. So I like all of those characteristics about it. And my hypothesis is that Flux was trained on a lot more realistic type images, and is probably better for this photorealistic use case than this generative vector graphic type use case. The one thing I did find while looking into this a little more was this cool blog post by Cross Labs talking about adding offset noise to your diffusion models. And they argue that some of these models aren't good at generating either really dark images or really light images. And they kind of, the way that the noise is added makes makes it so it distills it kind of in the middle here. And he gave like the very bare bones example of just trying to generate a solid black image with stable diffusion 3. And it even if you just trained it on black images, like that was, you're just trying to overfit to a solid black image with the current settings, it would generate something like this. So had a hard time generating a pure black image. And they made some tweaks to the actual adding of the noise where they added this little offset. Um, and they go into the math here of like why that actually affects it. But then they were able to generate super dark, more iconic light type things, super light, super dark. So I actually have an experiment running with this right now. I kicked it off like right before this session. Um, and we can tune into how this is working after we go through the code. Um, the other great thing about the Flux Kontext launch was they actually released a paper, which they hadn't released a paper for all of the previous models. And this was interesting to dive into because they did. Oh, here are some other fun examples of just like a reference character and putting it into different scenes. Super high quality. Um, but they did talk a bit more about the diffusion transformer that they have inside, and the kind of takeaway here is FLUX-1. All of the models are what are called a rectified flow transformer. It's trained in the latent space of an image autoencoder. And so before we dive into the code, I think it's good to level set on what those things mean. So hopefully you're familiar with autoencoders, but if you're not, here's a little refresher. It's basically a neural network where you have an encoder, you take in an image, you encode that down. So this is like a 512 by 512 by 3 channel image. You encode that down to a latent space. So maybe this is like 16 by 16 by some number of channels. So a smaller representation of the image. And then you decode it back up and you're trying to reconstruct the initial image from this latent space. And the hope there is that this latent space encodes things about the image, but not the actual image. So it abstracts away things like, oh, this is a vector art character and it's an ox and it's holding a coffee cup. Can you just reconstruct from those small set of numbers the image itself? And so what a lot of these newer diffusion transformers do, and this rectified flow transformer, is they will kind of strip off one half of the autoencoder during training and then strip off the other half of the autoencoder during inference. Um, and so during training, it looks a bit like this, where you have the input image and some text. In this case, they use two different text encoders in all of these Flux models. They use a T5 tokenizer, which is also another transformer. So this is like a encoder transformer model. Then they use a clip text encoder. Clip we've done deep dives on in the past, but this is trying to align text phrases with images. So kind of two ways of encoding the text here. They then encode the image as well from the first half of that autoencoder. So they get three different latent spaces here. They get like the image latent space, the T5 latent space, and the clip latent space, hoping that these kind of have, maybe this has more syntactic and semantic and has all of the attention to all of the tokens that you're putting in. And then this is like aligning the tokens to an image latent space. And then they do some fancy concatenation of all of those things. So you can see like the input latents and the conditioning latents, which is the text latents, going into this transformer block, that they kind of flatten all of those things out into a sequence so that the transformer can look at all of the latents and then output a new set of latents and have the model try to predict how much noise was added to this image. I guess I kind of glossed over this at the start, but you'll have the input image here. You'll add some level of noise to it. We'll see this in the code when we dive in. And then the goal of training is try to predict how much noise was added to the image, which we know at the start, we know at the end during training. And what's cool about that is if you train a model just to predict how much noise is in an image, during inference, you can just start with random noise and a text input. You then take away that autoencoder or the first half of the autoencoder that you have here, and just have like a noisy latent and the text latents. And then the diffusion transformer is going to predict how much noise was there. You can subtract that noise from the latent, run that through the decoder, and get an image out. And so the first time you get an image out, it's actually going to be pretty noisy again. And so you do this over a bunch of steps, and eventually you'll get like a clean image out the other half. And so the reason I bring this up is we're going to be writing code with T5 text encoders and clip encoders and this diffusion transformer. So just kind of wanted to give you a sense of how these things all wire up before we go into there. And so the two most common questions I get before fine tuning are usually just like, how many examples do I need and where do I get the data? Talked about it a bit above, but just want to give you guys a reference of what this data actually looks like. So for the dog fine tune, I have 22 examples here. I literally just grabbed these from my camera roll and uploaded them to Oxen into a data set. And then I took a visual LLM model. I ran it on that set of 22 images with just like a pretty simple prompt. This is GPT-4o mini. And I said, describe what the dog is doing in the image in 5 words or less, all lowercase, no period at the end. And that gave me a set of actions here. So now I have my set of images, my set of text pairs, really small data set, but that's kind of all you need to get started. The other one was a little more involved. This synthetic data set that I created for the Ox characters. We walked through how I did this a couple weeks ago for a more Pixar style Ox. But basically, I started with one reference image that I really liked. So in images, reference, I generated this guy, I think, with Midjourney originally. So he's a bit blocky. He's a bit of an ox. We call him Bloxy. And what I did was take a prompt that really encapsulates what this image is about. And then I had one model generate a bunch of actions. So like jumping rope, drinking coffee, wearing a blue jacket, with a green umbrella. And then I had GPT image 1 from OpenAI generate that character doing all of those things. And so this is kind of a fun way to get synthetic data if you want to go that route. You could totally just hire somebody on Fiverr to generate like 20 vector graphics of your character doing different things. And I think that would give you a good jumping off point. But this OpenAI image gen model is actually pretty good at following instructions too. It's just kind of a pain to use in some cases. One, because it's behind the OpenAI API, and two, it's really slow to generate these things. So the motivation, if you were to go this route, is to get a faster model, one that you kind of control end to end, and it's going to be cheaper than hitting the OpenAI API for these things. Like imagine trying to generate a video from just frames from OpenAI. That would be super expensive. So owning your own model there would be way cheaper. Any questions so far? Anything I'm missing in the chat, Scott? People are asking.
There was one comment about you can expand the data set by rotating images plus or minus 5 degrees to improve
Yeah,
source image fidelity.
yeah, that's a good one. You can do that like directly in the training pipeline, and we can talk about that when we get into the code. But yeah, lots of ways that you could extend this. Um, but I thought the synthetic data gen, which if you're curious, is also in the set of notebooks here. There's synthetic data.py if you want to try it yourself. But that's all in there and ready to go. So ran all these experiments on a single H100 in Oxen. It's actually pretty cheap these days just to rent an H100 in the cloud for a couple hours. So I didn't optimize for anything smaller than that. In theory, you can quantize these Flux models and train them on an A10 with only 24 gigabytes of VRAM, but I wanted just like a really dead simple example that we could walk through. And all of this will be writing in this Marimo notebook, which I'm enjoying for developing these things. The Marimo notebooks are just pure Python, a little easier to see the diffs on than Jupyter notebooks, and you can turn them into command line applications or web apps, making them really easy to run anywhere. Um, and so I'll kind of walk you through step by step how we train the model. So if you're not familiar, you can run these notebooks directly on Oxen, our platform here. Uh, and it pretty much, if you have a file in your repository that is a Marimo notebook, we'll detect that, add this launch notebook button. You can actually pick from a variety of hardware. You can customize the build script and install the dependencies that you need. And then you could crank this up to 64 cores and 64 gigs of memory if you wanted to, and give yourself kind of a max runtime so that you don't spend too many credits. But I will kick off this notebook and let's start going through the code. This full screen. Okay, cool. So a few things about Marimo. You can run it in app mode or code mode. We'll be in code mode here. This is like the most simple example. So there's a button to say moo 3 times. You can run it. It'll print out moo 3 times. And then you can also expose these things as command line utilities. So if you wanted that same thing to be able to run from the command line, you just write this like quick little entry point using a typer library, and then you can say if app mode is script, just run uh, the app, and that'll turn it into a command line app. But we don't need any of that stuff for us. And the first thing that we'll need to do is download all of the model weights. So Marimo also lets you have kind of like these generic user interfaces. So in this case, I'm going to import Hugging Face Hub and have the user import their or put in their Hugging Face API key. The Flux models are behind, let's see, huggingface.co. You have to accept the license to use any of them. So if you just went to, let's go to this one. You'll see you need to agree to share your contact information to get access to the model. So that's why we need to put in our API key here to download any of them. So let me grab that real quick. Put it in here. And then Marimo also has these nice features to add buttons so that you can kind of like kick things off and stop the execution of cells before you kind of go any deeper. So in this case, I'm going to add a load model button because this is uh, one of the more expensive operations that we have. And then you can say stop unless the button has been pressed, and then you can do the rest of your execution. And I like this especially when you're loading large model weights or like kicking off training jobs, just to have kind of like stopping points while you're writing the rest of your code, because it does take a lot of time to load these model weights into memory at the start. Um, So assuming we want to load the model, we will log into Hugging Face with the value that we put into here. That will allow us to download the model. And in this case, we're going to do Black Forest Labs FLUX-dev 1 as the main model. So that's all set up. Let's then define a function to load this model into memory. So there's a bunch of different components here that we'll have to load up. The first one is this Flux 2D transformer model. So this, if you remember from the Notion, is this big transformer block in the middle. It's Flux transformer model 2D. If you look at the actual files and folders in Hugging Face, you'll see there's like a VAE directory, a transformer directory, tokenizers, and encoders. So each one of these subdirectories have the model weights for the individual things that you need to load. So in this case, I'm saying, let's load this model from this subfolder transformer. And let's load it in bfloat16, which stands for brain floating point 16. This is like a cool data type that's slightly different than just your regular floating point number. It's a little, I don't remember off the top of my head, but it changes where you put the exponent in the mantissa, where you actually like save it on disk and load it into memory so that it's more performant for training neural networks, which is kind of cool. The transformer model is like one of the bigger models here, and it is out of all of the models that we'll be loading, and it is the one that we're training. So going to turn on gradient checkpointing for that as well. Then what we're going to do is add a LoRA to the Flux 2D transformer model. And this is because we don't want to train the entire thing end to end. We just want to train these LoRA weights that sit on top. That's going to make training a lot quicker. And it'll make the output model weights much smaller. And you can actually hot swap those out after they're trained, which is pretty cool too. So I have this little apply LoRA to Flux function. We're going to use the Q, K, V, and some of the feed forward layers as well. You just have this LoRA config, and you use this get peft model function from the transformers library to apply that to the transformer. So this will give us out a Flux model with a LoRA attached. And we'll make sure that we're just training these LoRA parameters or these parameters that are sitting on the side. The next thing we want to load is our variational autoencoder. So this thing is from the Notion doc, the one during training that's going to encode the image, and during inference going to decode the image. This thing is pre-trained. We're not going to be having gradients on this, and so we just put it in eval mode. And so we don't have any LoRA on this. We can then load the text encoders. So we have first the clip model, the clip text encoder. Remember at the bottom, we had these two T5 and the clip text encoders. So we need to load both of those guys. Again, all of these are just sitting in those subdirectories in that Hugging Face repository. So you need to also pass in what the subfolder is to load them. We have to load the tokenizers, and then I'm going to return all of this at the end in this big tuple so that we can unpack it. So there's kind of these, what is that, 6 different components that you need to run training and inference. And so it's the transformer, the VAE, the 2 text encoders, and then the 2 tokenizers that go with the text encoders. This, some unexpected indent. T5. There we go. I'm also just going to load all of my dependencies here at the bottom so that we don't have to worry about that. What's cool about these Marimo notebook cells is they also create like a directed acyclic graph of everything that's executing. So you don't necessarily have to put them in order. It scans the code, knows in what order it needs to execute it from what variables are there. So you can put things like all of your import statements at the bottom and kind of get them out of your way as you're developing. Cool. So that was most of the code to load the models. Let's use that and kick that off so that uh, it can be running while we're actually writing the training loop. Find this. You'll also notice I set up the LoRA rank and the LoRA alpha as parameters to this function so that we could play with different settings for that. I found 64 and 64 to work reasonably well. The larger this is, the larger the weights are that you are going to train. And in theory, you can imbue more behavior, but it is going to be a little less efficient. So now that we have that, we can load this model and you'll see it's now downloading all of these weights. They are like, if you go into the subdirectory, the transformer alone is, about 20 gigabytes. So this will take a second to download, and that's kind of why I did it first, so that we can let that cook while we go into training mode. So the next cell that I want to add is another just run button that's we'll have a load model and a train model button here. And this won't actually show up until this one actually finishes loading. But what's cool is once that's finished loading, we don't have to rerun it again to load it into memory, so it'll be quick. So for the running and training of this model, there are a bunch of hyperparameters that you can set up. And so we'll talk through this. I did grab this config from the AI Toolkit example. And so you'll see there's a couple interesting things here that I was playing with. There's a trigger phrase, which sometimes you'll actually just see this as trigger word. And some people just put in like some special tokens, like maybe we do like oxen spelled weird so that it can just learn that this word is what is going to trigger the style that we want. I actually didn't see that work really well for the vector graphic case. I actually needed to give it a pretty detailed prompt, even during training, to get it to generate anything that looked slightly like the character style that I wanted. So again, I think this is partially because Flux out of the gate doesn't do great on vector graphics unless you give it more context. But in the case of when I trained it on my dog, I actually just put like Finn the dog in here, and that worked really well. So in this case, we're going to do a pretty verbose trigger phrase, and we're going to be prepending this to all of the actions that we have in our training data set. So it'll be like this large phrase and then flying a kite. So you can see at the end here, it says like the ox character is, and then we'll put flying a kite or jumping rope or whatever. I also have where we're getting the training data from, batch size, gradient accumulation steps, how long we want to train it for. So this is how many steps we're going to do it for. Didn't experiment too much with learning rates or optimizers, but you can configure them here. Here's our LoRA parameters. And then this one's a fun one. As you're training, we'll also set up a sampling loop so that we can kind of debug as we're going along. And to give you an example of what that will look like, I actually have a model training right now, this one that I was experimenting with this noise. And let's check in on it to kind of show you. So as it's going, it's saving these LoRA safe tensors as we're going along. And then it's also saving some sample generations in the README just for debugging. And so you can see like the first iteration, it's definitely following the prompt, but doesn't have the style yet. Second iteration, maybe it's trying to get some square bodies. It's getting the line a little better. But again, it just like really takes a while for this Flux model to learn this style, which I thought was pretty interesting. And my main takeaway from these experiments. So that's what these will do is like you can configure what samples we want to save out the other end. And so with that, let's get into the core training loop. So we will define a function called train. This will just take in the model that we loaded before and this configuration dict. Again, probably define these in the configuration, but the device, we're going to be running this on the GPU, and the data type is that brain float 16. And the first thing that we'll need to do is actually load this data set from Oxen and download both the Parquet file that we had defined here. And then this Parquet file references a bunch of images, which we have in this subdirectory of like images generated. And so kind of tie the labels to the images through this Parquet file. So those are the two things that we're going to be downloading. And I created this nice Flux dataset class to do all of that. It'll inherit from just a PyTorch dataset. So if you've ever implemented a PyTorch dataset, you kind of need to implement two things, which are the size of the dataset and the length of the dataset. And so let me get these in here. That's a little preamble. But there's two main functions that you'll need to implement in here, and it's the length function and the get item function to make this thing iterable. So the length and the get item. So what we do is take in that configuration. This remote repo is a Oxen.ai specific thing. You could grab your data from anywhere. We happen to have them in this Oxen repository right here. There's different resolutions that we'll want to sample at. So that's what this resolution stuff does. And then we can just take this repository, download the images from that images path, and download the data set. So the train.parquet from this dataset path. We then load in the Parquet file just using pandas, iterate over all of the rows, grab the image, grab the action. You can add different transforms in here. So this is similar to what was said in the in the comments before. You could add like shifting and rotating and all sorts of transforms. I just kept it pretty simple here, and this is just normalizing the image as our only transform. And then we'll save that in image files and captions in these arrays, and then use those in the length and get item functions. This is pretty simple. The length of the data set is just the number of files that we loaded. And then get item is actually where we load the image from disk. So we don't do that all right away to save some memory. And then this is also where we prepend whatever trigger phrase we had in the config above. Flux does require you to have images that are divisible by 16 in size, just because of the way that all of the modules wire together. And so each item here is going to return the actual image, the caption, and whatever resize transform that we did. So again, we're training this on a bunch of different resolutions. And so we'll return whatever that new width and new height is. And you could do any of those noise operations within here because we call self.transform, and it'll just kind of run through all of these transforms when it loads that example. So that's all for loading the data set. Once you have the data set, we then need to put it into a data loader. This is also just a PyTorch thing. This makes batching really easy. In this case, we're actually just using a batch size of 1, so don't necessarily need to use something like this, but it is good to know if you wanted to configure this batch size to be a bit bigger, the data loader helps turn your data set into something that can be batched. We will then load the model here. We might actually even want to do that as the first thing. Not that the order really matters, but just in case this fails as we're loading. So remember, we loaded this as just like a tuple with all of those 6 things that we needed: the transformer, the VAE, text encoders, and tokenizers. And then we need to make sure that the transformer has gradients and we can train it. So if you remember when we were setting up these models, we did mark some of them as just eval. It's good just to make sure that the transformer is marked as train before you kick these things off. In order to generate the noise as we go along, there is a noise scheduler. And specifically, I guess I could put this all in the training loop here, just so we're not hiding too many functions. Stable Diffusion 3 and these rectified transformers use what's called a flow match noise. So we have a flow match Euler discrete scheduler. And this is based off of the Stable Diffusion 3 paper, which introduced these scaled rectified flow transformers. And so this is important during training to have the right noise scheduler as we're going along. And Flux specifically had a few more parameters in here for like shifting the noise in a way. And they claim that this does help with the darkness and the lightness, like we talked about before, but I actually didn't see it work super well, at least with these parameters. Cool. Once we have the noise, let's go back to training loop. We can set up our optimizer. In this case, we're using Atom 8-bit. If you wanted to use Atom, just regular Atom W, it does just take up a bit more memory while you're training. The 8-bit worked pretty well for me, but that'd be another interesting thing to try, which I haven't yet, to see if we can fix the actual generations there, maybe using a full precision optimizer. Then we'll set up the learning rate. You could have different schedulers for the learning rate. We'll just have it be a constant learning rate here, but it's nice to like have this be a learning rate scheduler and not just a raw number in case you want to swap that out. And then the way that I've been saving all of these experiments, which you can kind of do this however you like, but I've been saving them on the Oxen repository itself with a very special branch name. So if you look, I've run a bunch of different experiments here with different LoRA ranks, and I've just been dumping all of the weights to these branches in this output directory. So basically all this is doing is just seeing how many branches we already have, adding the experiment number at the end, and creating a new branch with that branch name. So let's get into the training here. I know we're kind of running out of time, and I will share all of this code when it's done, but I want to give you a bit of just how each one of these steps work. So we'll iterate over for just number of steps all of the batches in our data loader. So the reason that we did that get item and length before is so that we can just put this data loader in a for loop and grab the batches out. If we've gone beyond the number of steps, we'll just break. Within this batch, we can grab all of the images, and I'm just doing a little debug logic here just so we can see how things connect to each other. I'll kill that for now so it's a little cleaner. But the first thing we do is take our variational autoencoder and encode the images. This will give our latents out. And I noticed in the AI Toolkit, they also scaled these latents to normalize them a bit and make it a bit easier to train. So you could just go on the raw latents. This makes it a little easier to train. We then encode the text of the caption. So there's the two models that we have here. We have a text encoder 2, tokenizer 2. Actually abstracted that into another function here, so it was a little easier to follow. So I'll put that down here. Second. So this takes in our tokenizers and our text encoders just as these pairs here. There's the clip encoder and there's the T5 encoder. So you have to both tokenize the input and pass them through the encoders. I thought this was pretty interesting, the way that they chose to grab the embeddings from each one of those models. For the text encoder, they grab what's called this pooler output at the end. And for the T5 encoder, they grab the last hidden state. So other things that you could potentially play with is like where you grab those actual weights from the different models, but they did a couple experiments, and those are the best places to grab the actual latents. So that's going to be our encode function that runs the text through the two tokenizers and through the two encoder models to give us out our what they call the prompt embeddings and the pooled embeddings. So the prompt embeddings are from the T5 model, and the pooled embeddings are from the clip model. Once you have those encoded, we then have to add the noise. And this is an important and interesting part of the training loop. So what we'll do, since we want to be able to denoise over time, we're going to set a number of time steps and just randomly generate some noise, either a lot of noise or a little noise, within this range of time steps. In their code, they used like 1,000 different time steps, so 1,000 different levels of noise. And basically just use the torch.rand like function given the latents to generate the initial noise. Then they scale this noise based on whatever time step that we're on and have a very specific way of adding it to the noisy latents. And this is where the rectified part of the transformer comes in. We don't have to dive too much into this. Is just like picking whatever time step of noise we're in, but this is the juicy part right here. And if you look, it's actually just like a straight line. So it's like if you remember y equals mx plus b from your algebra classes, this is kind of a version of that. And what they're saying here is they want the noise to be able to kind of be decoded in this linear fashion. So if you want more details on that, check out the Stable Diffusion 3 paper or the Rectified Flow Transformer paper. But this is how we go from the actual latence and just some random noise to this kind of more linear noise that we're adding at each time step. And again, each time it comes through this loop, we're just going to pick like a random time step and apply that amount of noise. So sometimes it'll be a little noise, sometimes it'll be a lot of noise. And you do that enough throughout the training process, then during inference, you can say, remove the noise, remove the noise, remove the noise, remove the noise, and get to an actual image. You have to pack this noise into a very specific format for the transformer to take it in. So I'll actually put that right here. Again, grab this from the AI Toolkit, but wanted this to just be a single self-contained example. Then we have to grab our position IDs for the image and the text. So if you remember in a transformer, you also have these position embeddings of where items are during training. So we have to have position embedding or position encodings for both the images and the text. So that's what this part does. And then finally, we can do the forward pass through the transformer. This is one thing that tripped me up a couple times as I was trying to do this from scratch is the transformer module itself. So if you look at like the Flux transformer 2D model, just search for this real quick. Flux transformer 2D. It has a bunch of different things that you can pass into the forward pass. And you'll notice one of them is this guidance parameter. The initial example that I went through had a guidance of like 3.5, and I was getting really blurry images out the other side. I changed that to be 1.0 during training. This is actually just how well the text guides the image generation. But if I had this any higher, I would get super blurry images out the other side. So just have a comment in there that to use 1.0 here, I think could use a little more experimentation as to why that is the case. But basically, you're passing in your noisy latents, whatever time step that you're currently on, the prompt embeddings, the pooled embeddings. So this is clip in T5, the positional IDs for both the text and the image, and then this guidance parameter. And you're going to get a prediction out the other side that is the predicted amount of noise. And so then our loss function is actually pretty simple. After this, it is just so the target image is going to be, or the target latent space, I guess in this case, is going to be the noise minus the initial latence. So we know the noise that was passed in, we know the latence that came out of the BAE. This gives us our target. And then we're just doing like a mean squared error between the predicted noise from the transformer and the target here. And then this will give you could give you a batch out. So if you want that just to be a float, you can take the mean of all of them. You then run dot backward to do the backward pass. I did find that this gradient clipping helped as well. And you usually run that right after the backward pass and before the optimizer step. So that's an important thing to add. And then you take that atom optimizer and actually this computes all the gradients, and then this applies all the gradients to the model to update all the weights. So that's like the core training loop there. We're running out of time, but I will be putting all of this code up, and it's around like 500 lines. So if you want to go through step by step and see all of those things um, that I did within the code, I think this is a much easier example to follow than the AI toolkit. We'll also be putting a blog out where I explain all of these things. But at the end, we did get some pretty encouraging examples for the dog, a little less encouraging for the vector graphic. And my takeaway is that, at least for the vector graphic use case, PixArt is actually a better model. And I thought that was just interesting that the small model, you might not want like the huge pre-trained one on everything if you have a very specific use case, and always look at the license. So with that, I think we have to call it a wrap time-wise, but happy to hang out and answer like one question at the end. Oh, Greg B actually had a good note in here. You need to keep the guidance at 3.5, but to ensure your config scale is at 1. Using a guidance of 1 will wash out the results. Might well work well with vector type training, but not so much with photos. Oh, interesting. So, Greg, I don't know if you can hop on at all, but there's like two places that you can pass in the guidance. There's the during training, like that embedding guidance, and then there's during inference. There was also guidance, and during inference, I passed in 3.5, but during training, I actually just had to pass in 1. So I don't know if you have any intuition there. And if you can't chat, maybe we'll just talk in Discord too.
We might lose. Oh no, he's coming on. Greg, we can't hear you if you're talking. See the mic is off, is unmuted. Still can't hear you if you're chatting.
All good. If not,
And then
um,
take a minute, another
Oh,
question.
yeah, I have one more question. Can we generate vector images with transparent background with fine tuning?
yeah, so you would just have to make sure that you load in the alpha channel while you're
Mm,
training the model. You'd have to do you'd have to make sure that all of the transformer blocks line up with that. Actually, don't know off the top of my head if it was pre-trained with the alpha channel at all, so you could experiment around. I actually don't know off the top of my head.
I see. Thank you.
Yeah. All right. Cool. Well, I'll kill the recording here. Thanks if you're watching on the YouTubes.